For part D, we're given the function a is equal to 10 times 2 raised to the t divided by 5. So we'll go to y equals, clear out our old function, enter the new function 10 times 2 raised to the x divided by 5. Make sure that the x divided by 5 is in parentheses. Otherwise, the calculator will raise 2 to the x power and divide the result by 5. We'll go back to our table, second graph. Our initial quantity is 10, and we see that the y values are increasing, so we want to check and see how long it takes for 10 to double to 20. Well, we find 20 at x is equal to 5, so it took 5 units of x for the y to double from 10 to 20. So let's go back to table set to check and see if there is a fixed doubling time. We'll leave the table start at 0, but we'll change our increment to 5 since we noticed that it took 5 units of x for the initial quantity to double. We go back to our table, and we notice that as x increases by 5, the y values are in fact doubling. Twice 10 is 20, twice 20 is 40, twice 40 is 80, and so on. So this function has a fixed doubling time. In E, we're given the function p is equal to 500 minus 1/2 t. So go to y equals, enter the new function 500 minus 1/2 x. Go to table set, enter a table start of 0 and an increment of 1, and then go back to the table. Notice that this time the initial quantity is 500 and that the y values are decreasing. So we want to check and see, does this function have a fixed half-life? Well, half of 500 is 250, so we want to scroll through the table until the y value is 250. Now notice that the y values are going down rather slow, so instead of incrementing by 1, we might choose a larger increment. Let's go back to table set, and let's select an increment of 100. Go back to our table, and we're looking to see where the y value is 250. The y value is 250 when x is 500. So it takes 500 units of x for the initial quantity to be cut in half. Does this function have a fixed half-life? We go back to table set, leave our table start at 0, and change our table increment from 100 to 500, which was the initial amount of time that it took for the initial quantity to be cut in half. Go back to the table, and we notice that as x goes up by 500, the y values are not being cut in half. The y values are going down by 250. So initially half of 500 is 250, but half of 250 is 125, and that does not occur when x is 1000. So this function does not have a fixed half-life. Finally, in part F, we're given the function n is equal to 50 times 1/2 to the t divided by 20. So go back to y equals, enter the function 50 times 1/2 raised to, again remember to put the exponent in parentheses, x divided by 20. Set up a table. Going to start at 0 and increment by 1 initially. Then go to the table. We see that the initial quantity is 50 and that the y values are decreasing. So we want to check and see how long does it take for 50 to be cut in half to 25. Well, the y values are decreasing rather slowly, so again we might use a little bit larger increment. Let's go back to table set. Instead of incrementing by 1, let's increment by 10. We go back to our table, and we can see that the y value is cut in half from 50 to 25 over 20 units of x. So as x increases by 20, the y value is cut in half. So let's check and see. Does this have a fixed half-life? We go back to table set, leave our starting value at 0, but this time increment by 20. Go back to the table. As x increases by 20, the y value is cut in half from 50 to 25, and then from 25 to 12.5, from 12.5 to 6.25, and so on. As x increases by 20, the y values are cut in half. Therefore, this function has a fixed half-life. One of the things that you might notice is that for a and d, we had a fixed doubling time, and for a and d, both of these functions are exponential functions with a constant growth factor. In this case, we have y is equal to 6 times 2 to the x. The growth factor is 2. 2 is bigger than 1, so this one has a fixed doubling time. For part D, again, we have a exponential growth function. Our growth factor is 2 to the 1/5 power. Looking over our answers, we might note some important concepts. In A and D, there was a fixed doubling time. What did the functions look like for A and D? Well, each of them are exponential functions, and in particular, they're exponential growth functions. So exponential growth functions have a fixed doubling time. What about the ones that were neither? What about the functions that had neither a fixed doubling time or a fixed half-life? Well, b is a linear function, and e is also a linear function. Linear functions do not have a fixed doubling time or a fixed half-life. What about the ones with a fixed half-life? In part C and in part F, we have exponential decay functions. So exponential decay functions have a fixed half-life.